All righty, so today we're going to start with vapor pressure. So we're going to start with vapor pressure. Okay, so we see a little experiment here that was performed. So you see you have these two containers under glass. One of them has a solution in it, one of them has a pure solvent, so this time it's water. And you notice how the solvent container will empty and the solution container fills up. That's because the pure solvent has a much higher vapor pressure than the solution. The solution is trying to stabilize itself, so it keeps taking in, it's trying to lower the vapor pressure above itself, so it keeps taking in those solvent molecules, and eventually you just do a transfer the solvent from one container to the other. That's because so vapor pressure of a solution is lowered when you put a non-volatile solvent into a solute into the solvent. Again, I'm going to have issues with words that sound very similar. So again, vapor pressure, and that's the pressure of the gas above the solution or the solvent. So how many of those molecules are in gas phase? So, and what did we say volatile was? Not explosive. Well, I want to ask you. Nope. Volatile solvents and solutions have a very high vapor pressure in standard conditions. So, for example, acetone is volatile. As you drop acetone on your skin, it evaporates immediately. It's pretty much all vapor in standard conditions. That's volatile. All righty, so we can start working with this concept by using what we call Raoult's law. So the vapor pressure of your solution is going, and what is that? What is that symbol there? What is that? It's mole fraction. So yeah, the mole fraction of your solvent multiplied by the vapor pressure of your pure solvent. What does that mean? Pure solvent. Well, water can be a solvent, but what would the pure solvent be? You can either have a solution with stuff in it, or you can have the pure solvent with absolutely nothing mixed into it. So it's like, what would the vapor pressure of the pure solvent be if there was nothing mixed in it? Usually you can have tables that can tell you that for given temperatures. Okay, so let's say we have an aqueous solution containing glucose. It has a vapor pressure of 19.6 torr at 25 Celsius. What would be the vapor pressure of the solution at 45 Celsius? The vapor pressure of pure water is 23.8 torr at 25 Celsius and 71.9 torr. That's 45 Celsius. See, these are constants that you can look up. If the glucose in the solution were substituted with an equivalent amount of sodium chloride, what would be the vapor pressure at 45 degrees Celsius? Okay, so what we can do is we can say, well, I can use my 25 degrees Celsius numbers and I can figure out the mole fraction of the water. Because then it doesn't matter if I change temperature, mole fraction is not going to change. So our mole fraction, that is going to be the vapor pressure of the solution. So at 25 Celsius, it's going to be our 19.6 torr over our 23.8. So our mole fraction is 0.285. So now we know that mole fraction doesn't change, so at 45 degrees Celsius, so in here we put our 0.825, and then at 45 Celsius, the vapor pressure of pure water is 71.9 torr. The vapor pressure of our solution is then going to be 59.3 torr. Okay, so that's with glucose in the water. Now, they're trying to trip you up with this problem. Why would they switch you from glucose to sodium chloride? What does sodium chloride do in solution that glucose does not? Yeah, so it not just dissolves, it what's the word? It dissociates. So if I put 1 mole of sodium chloride in solution, how many moles of particles do I have in solution? 1 mole of sodium chloride goes in, I have 2 moles of particles. Because it splits into its constituent ions. So you have to make an assumption here. So the thing we want to know is we want to start figuring out mole numbers. So I'm going to start with 100 moles of glucose. Okay, solution. We'll just call it the solution. All right, now so you remember this is going to be moles of H2O over moles of solution. So then we can solve. And so this would be our 0.825 times our 100 moles. We are going to get 82.5 moles of water in this solution. Now, let's figure out how many moles of glucose we have. Total moles minus moles of the water. So 100 minus 82.5. This will give us 17.5 moles of glucose. We need this because that means we're going to put in 17.5 moles of NaCl. However, in solution, this 17.5 moles of NaCl becomes, or 35 moles of particles. Because again, that NaCl is going to split into sodium and chloride. So I should take the number of moles of the molecule, the dry molecule that I put in, and multiply it by 2, so I can account for the number of particles in the solution. Okay, now let's redo the mole fraction of H2O. So it's going to be an H2O plus moles of ions. All right, so Moles ratio is 82.5 plus 35.0. We now have a mole fraction of 0.702 for the water. So the vapor pressure of this solution, that is going to be, so again, we have our mole fraction of water, vapor pressure of pure water at 45 Celsius, and that's going to be 0.702 times the 71.9 torr. So this time we'd have 50.5 torr as our vapor pressure of solution, which is going to be less than the vapor pressure of the sugar solution. Because again, you have more, so the solute you put in broke into constituent components, whereas the glucose did not. So now you have more components, more non-volatile components in the solution. That's naturally going to decrease the vapor pressure. Okay, so ideal and non-ideal solutions. So the total vapor pressure of a solution is going to be the partial pressure of each individual component of that gas. And so you can just sum together the Raoult law for all of these vapor pressures and get the total pressure of the solution. Now, you see you have two graphs here. An ideal solution follows a straight line, the straight lines. That's going to be your Raoult's law will actually calculate the straight lines. So the straight lines are formed when you have similar, so you have interactions between the solute particles, interactions between the solvent particles, and then when you mix them, you have interactions between solute solvent. And when you have similar interactions amongst all of those, you're going to be very close to the straight line or an ideal solution. However, you get a negative deviation. Let's see, which one is that? Going to be the one on the right, negative deviation. When your solute-solvent interactions are stronger than the solute-solvent or solvent interactions. So it wants to be a solution more than it wants to be either the solvent or the solute. And then your positive deviation will be the opposite. Your solute particles, your solvent particles will interact more strongly than they will with each other. So take, for example, again, let's see. You'd get for example, you get a positive deviation if you mix oil with water. Because again, your oil is your solute and your water is your solvent. So your water is going to have much stronger interactions with other water molecules. And the oil will interact with itself more strongly than water and oil will interact with each other. That's going to be a positive deviation from an ideal solution. Versus, I'm going to take a guess on this. I would say kind of like the whole idea of throwing a salt into water. Because within the salt itself, it's crystal, you're going to have ionic interactions. In the water, you're going to have dipole and you're going to have hydrogen bonds. But when you throw them together, now the solution has hydrogen bonding dipole and ion dipole interactions. So you're getting a stronger interaction, so you're going to get a negative deviation. Okay. So let's see, we have a solution prepared by mixing 3.3 moles of, can anyone name that? CH2Cl2. Can anyone name that? So what's CH4? Huh? Nope. That's NH4, it's an ion. Methane. So yeah, what say what? So what kind, so you're missing one prefix, dichloromethane. Like in this one, methane is your base molecule, and you're going to just replace two hydrogens with fluorines, you get dichloromethane. So the other one is dibromomethane. And so then you have the 0.5 moles of the dibromomethane at 25 Celsius. Assume the solution is ideal, which means that we can use Raoult's law directly to calculate this. We're not going to do any calculations outside of the ideal situation because the math just gets nuts. But at 25 Celsius, vapor pressures of dichloromethane and dibromomethane are 133 and 11.4 torr respectively. And I hate to do okay. I think very highly of everyone's intelligence in here, but I have to check because, for example, I just found out that there are people going to like Ivy League schools with full scholarships who are completely illiterate. I never thought we would have that issue. So do you guys know the meaning of respectively? Okay, so it means that your dichloromethane will be the 133 and your dibromomethane will be the 11.4. So it's just I've never run into an issue here that I've ran into at other places. Like students who come here are usually pretty well prepared. I just can't believe we have a thing going on where there are large campuses in this country where students are completely illiterate. I didn't think that was possible. Also, I didn't think I'd be arguing with people in physics class that the earth was flat. I thought we solved that in, I don't know, the 1500s. Apparently it's a thing now. All right, so what we're going to do, we're going to have to use for the total pressure of the system, we're going to have to find the partial pressures of each one of these. So we want to know the partial pressure and solution of each one of these compounds. Okay, so and then let's calculate the composition of the vapor pressure in mole fractions. So what we're looking for is that and that. Now, you're going to see some superscripts on these. These are used throughout the book. They don't mean anything except this was calculated as a vapor. So V is calculated as a vapor. So like this would be, we're worried about vapor composition. We can also have mole fractions in terms of the liquid phase. So okay, so my total pressure will be my partial pressure of dichloromethane plus my partial pressure of dibromomethane. And so this is what we're going to get because we're calculating for the solution, okay? So this is where we're going to use our mole fractions in the liquid phase. Okay, so we're setting it up like this. Okay, so let's find out those mole fractions in the liquid phase. Okay, so this is going to be so 3.3 moles, 0.5 moles. Okay, so I need total moles. Okay, so we're going to have why did I use 0 free? Am I supposed to write down 0? I wonder if I typed it wrong or I wrote it down wrong. Yeah, by the way, we're going to use the numbers that are there. So someone get out your calculator because I put an extra 0 in. What do we get for this? I would think it's still going to come out to be about 0.375. Okay. Okay, so I just, for some reason, wrote an extra 0 in when I was writing this down, but that happens. Okay, so we have the mole, that mole fraction. Let's do. Now, what's a fast way to find the mole fraction of the dibromomethane? I could go ahead and just calculate it the same way, but I want to make sure we understand this concept. In the solution, the mole fraction of dibromomethane plus the mole fraction of dichloromethane is going to equal what? 1. It's going to be 100%. Mm-hmm. So 1.0. So we're going to have 1 minus the mole fraction equals the one that I'm after. And that's going to give me 0.625. And these are my liquid. So now these are going to be my liquid mole fractions. So now I can solve for my P total. All right, so what I'm going to have I have to have my mole fraction of my dichloromethane times its pure pressure. Okay, so it's going to fill in like this, 0.375 times 133 torr plus, now we'll do the dibromomethane, 0.625 times 11.4 torr. Our P total then is going to come out to 57.0 torr. Okay. Now, we can solve for one of these mole fractions in the vapor phase. Does anyone remember how this equation alters for the vapor phase? Let's see, is that number a moment? Something that's going to help you. Nope. So for vapor phase, what mole fraction also represents as the partial pressure over the total pressure. So for the CH2Cl, that's going to be the 49.9 torr over the total 7.0 torr, and I'm going to get 0.875 for that vapor pressure, for that mole fraction in the vapor phase. And I'm going to go ahead and solve for the other one in the way we just used. So we found the mole fractions of each of these compounds in the vapor above the solution. Remember, Raoult's law is calculating using mole fractions from the liquid phase. So that we had to translate that. Now, I'm sure going through all these Raoult's law calculations has left most people going, are we super duper for real right now? I don't want to do this. It'll take some practice. So we'll have a little fun with some, like, again, these are kind of like what you'll see on your exam. What do we think for these? Ah, it is. No, not okay, so B. B. B is the answer. So imagine you have your pure solvent. It has a certain vapor pressure. You dump salt in. So over time, the vapor pressure is going to decrease because that's what you not all solvent. It's all you does. What about the second? Oh, yeah, I didn't put the whole question on there, did I? Darn it. Okay, well, you actually can't answer that one. So there's supposed to be a list of solutions. Here I thought I had brought that across correctly. No guarantee that that shouldn't happen on the exam, but if it does, that's a free point. So you kind of want that to happen as much as possible. If I did that 30 straight questions, you all get a perfect score. I wouldn't count on it. Okay, now we're going to start talking about what we call colligative properties. These are properties of solutions that depend only on the number, not the identity of the solute particles. So the first one we have is boiling point elevation. There's not a ton on this in the book because it's one of the least commonly used laboratory procedures. In a lab, you're more likely to see freezing point depression than you are boiling point elevation. But you dump a non-volatile solute in, and the boiling point of the solution goes up. And so your equation for this is going to be your delta, your change in temperature is going to be your KB, and that M, what do you think that M is? Lowercase m. We've talked about it. We did a calculation on it at the beginning of this chapter. The KB is a constant. It is molality. So remember, that's moles of solute per kilograms of solvent. And the K is your molo boiling point elevation constant. And so that'll be degrees Celsius per molality. So degrees Celsius over little m. Okay. So here's a look at a curve where the boiling point increases. So you remember the normal boiling point. So you see a problem that says normal boiling point. You know that you're at 1 atmosphere or 760 torr. Okay. So you dump in a non-volatile solute, and the point at which that 1 atmosphere of pressure above the solution is achieved is at a higher temperature. This one, I want you guys to work on this for a few minutes. These colligative property problems are really straightforward. Just want to see if you can figure it out. Question though, molar mass is in what units? Grams per mole. You're trying to find grams per mole. So remember your units for your mole constant. So your temperature, your delta T is going to have to stay in degrees Celsius. And also keep in mind, there are sections of this chapter, subsections that I'm skipping because it's stuff you can go read. But keep in mind, all of it's fair game for quizzes. Now, the stuff we're doing today, of course, won't be on the exam, but Did anyone get an answer? Remember, in this equation here, there's only one of those quantities I can get moles out of. As you notice, I already have 2.0 grams of the sample. So which one of those quantities can I get moles out of? We're going to use that, but just in that equation, which one of those can I use to get moles? A molality. So we're going to rearrange and we're going to say, so what, our delta T and then our KB is our 5.03. And we see kilograms per mole. This is going to give us 0.268 moles of our biomolecule per kilogram of carbon tetrachloride. Okay, so I'm going to take that per kilogram. 1 kilogram is 1,000 grams. And then I have the 15.0 grams of my CeCl4. That's going to give me 0.00402 moles of my biomolecule. Okay, and then I have 2 grams of it. So my molar mass I'm going to get a biomolecule that is 498 grams per mole. So a lot of these problems that you work with colligative properties are going to seem a lot more difficult than they really are. Like, don't overthink them. Okay, that was boiling point elevation. This one here, this is the one you'll see more as a laboratory procedure, freezing point depression. Again, you dump in a non-volatile solute to any solvent, it's going to lower the freezing point. So for example, you dump a bunch of salt into water and it now freezes below 0 Celsius. All right, so the freezing point of T-butanol, or the tertiary structure of butanol, you're going to learn about all these structures in organic. Your end structures are usually a straight chain. Your tertiary structure is particularly noted by the hydroxyl functional group on that central carbon. But you have 25.5 degrees Celsius. The mole freezing point depression must have been one of those days. Elevation constant. No, it is depression. Boiling point was elevation. Never mind. Okay. Freezing point depression constant is 9.1 degrees C, kilograms per mole. Usually T-butanol absorbs water on exposure to air. If the freezing point of a 10-gram sample of T-butanol is 24.59 degrees Celsius, how many grams of water are present? Which one is the solute? The T-butanol is going to absorb water in the gaseous phase. Which one is the solute? Well, actually, no, it's going to absorb water from the air. That's what it's saying. So water is going to be in solution with it. Which one's the solute? Which one's the solvent? Yeah, so butanol is the solvent. Yep, because it's pulling the water out of the air. Okay, so this one, I mean, sometimes you can draw yourself a little map. So how many grams of water are present? Well, I know, well, I said this, I said I can start with molality. Then I can go to moles of water and the grams of water. So I'm going to do a very similar calculation. All right. Molality is going to be 0.10 moles of water per kilogram of T-butanol. Okay. Well, let's see, 10 grams of T-butanol. Okay, so and I can do this as one long calculation. Maybe give myself a little more, crowd it like that. Okay, so then I have 0.10 moles H2O per kilogram. What kind of compound is T-butanol? Does anyone know? Think of how the word sounds. And then what in a mole of water? When I calculate this, I get 0.018 grams of water. So I mean, T-butanol, it's made by removing a hydrogen and slapping on a hydroxide. Think of the end of the word. What kind of compound is that? An alcohol. We won't really get to work anything about this today, but your last colligative property is called osmotic pressure. So the way you think about this is you have like your tube system here with a semi-permeable membrane in the middle that will allow solvent through, but not solute particles. So again, those solute particles are going to start to collect more of the solvent. One of the sides is going to increase in its volume, the other side will decrease. The osmotic pressure is the pressure that's needed to force both sides back down to the same volume or to stop osmosis from occurring. So when you press down, you're going to get a reverse osmosis. That is your osmotic pressure. And it's represented. So what is that letter there? That's a Greek letter pi. So Greek P, pressure. So, and then your MRT, M is molarity, so grams per mole. R is your ideal gas constant, and T is temperature in Kelvin. So we'll work with this, well, I guess on Monday, because Friday is D-Day, so.